Welcome to the Space Telescope Public Lecture Series. Tonight's topic, black holes. How do we see that which gives off no light? From Stephanie Massa of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at STSCI. I will remind you that our public lecture series will be online only throughout the rest of 2022 and into 2023. As always, I like to thank our wonderful tech team, Thomas Marufu and Grant Justice, who bring you these pictures, bring you the lectures. Our upcoming talks next month, high energy astronomy with the Swift Observatory. And this is a brand new topic for us. We've never discussed this in our lecture series, so this is going to be great. Steve Kirby from Penn State University. And for January and February, I'm a little behind in actually nailing down a speaker for those. So we will have fascinating topics, insightful speakers, or insightful topics with fascinating speakers for both January and February. If you would like to know what those are going to be, you can check back on our website where they will be posted, www.stsci.edu/public-lectures. This is where you will find all of the information. On the left-hand side, you will see links to our webcasts, both on our YouTube playlist and the webcast archive here at STSCI. On the right, you will see our email, which is basically 2 emails a month reminding you about the lectures upcoming. You just enter your email address and hit the subscribe button. And as promised, all of the information about our upcoming lectures is posted here. If you click on one of those lectures, you get the full details, including the description of it. And after it has been recorded, the link to the STSCI webcast, as well as its recording on YouTube. For our email, as I said, the easiest way is just to sign up for our announcements on our website. But you can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope. And if you sign up for that, you will get new video notices and reminders of live events such as this. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. As always, I remind you of our social media. We are on Facebook, Twitter, YouTube, and Instagram for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute at all of the addresses there. I myself do a tiny little bit of social media, and you can find me on Facebook and Twitter. And now our news from the universe for November 2022. I'm only going to do one story tonight, but it's quite the story. It is the pillars of creation. Now, you may remember that way back in the 1990s, we produced an iconic image from Hubble, the pillars in the Eagle Nebula, that got the nickname the Pillars of Creation. And these pillars, I think the one on the left-hand side is about 3 light years long. There is energy streaming down from above that's blowing away the low density gas, leaving behind these pillars. And in the tops of these pillars and along the pillars are places where stars are being born. And this was one of the very first Hubble images that really caught the public's attention and said, wow, this telescope produces amazing imagery. And the public started following the attention. Well, 20 years later, we took this image of the pillars of creation with a new camera that was on Hubble, Wide Field Camera 3. The first one was taken with Wide Field Planetary Camera 2. And it was a much larger image, more detailed because it was a newer camera. And again, this amazing image of these pillars inside this nebula. But Wide Field Camera 3 had an improved infrared mode on it. So we were also able to get a near infrared view of the pillars. And as you can see from this, that the pillars that appear solid and dense, invisible, actually appeared a little bit more wispy because infrared sees into the pillars. The longer wavelengths of infrared see through some of the gas and dust into the and through the pillars. You also notice the tremendous number of stars that you see here that you don't see in the visible light image. So that's the setup. And now we have the Webb Space Telescope up there. And it looks in the near infrared and the mid infrared. So of course, Webb is going to look at this. So this month, we released this near infrared view from Webb. Boom. Yeah. Yeah, look at all that detail in that gas and dust that you do not see in the Hubble image, but comes across really strongly when you look at it with Webb. Webb has higher resolution, higher spatial resolution, and also Webb can get more photons. Its light gathering power is stronger. Also, the other thing that makes this more colorful is Webb has many more filters in the infrared than Hubble does, so it can create a wider spectrum view in the near infrared. But this is just the near infrared. As a special Halloween treat, last Friday, we released the mid infrared because that looks like a bunch of ghosts. It has a ghostly feel to it. Now, you'll notice one thing, that there aren't that many stars in the mid-infrared. If we go to the near-infrared, you see a ton of stars. You go to the mid-infrared, you see fewer stars. That's because the emission from starlight fades away as you go to the mid-infrared. Not that many stars actually shine in the mid-infrared, but the gas and dust shines really, really well in the mid-infrared. So you have even more detail in the mid-infrared than you do in the near-infrared. But what I've showed you is all of the images co-aligned. And basically, all 5 of these images are on the same spatial scale so that we can blink back and forth between them and see them. But one of the things I want you to understand is that these different instruments that have done these different observations have actually very different resolutions. So here is actually these 5 images on the same pixel scale. And you can see that the near infrared image that what we released from Webb this month has as many pixels, more pixels than all the other 4 combined. Yeah. So the amount of pixel information we got from the Webb near infrared is amazing, right? And you will notice that the very first WIF-PIC 2 image up in the top left, that doesn't have that many pixels compared to things, right? And so that going to the WIF-C3 was a huge improvement. Then you've got the near infrared and the mid infrared. The near infrared from Hubble and the mid infrared from Webb. Those are actually smaller because as you go to longer wavelengths, you lose resolution, okay? The resolving power of a telescope is proportional to the wavelength you're looking at. So that MIRI image, which looks so small down there in the bottom left, is actually looking at wavelengths that are 10 to 20 times longer than the Hubble visible light image. Therefore, its resolution is going to be much, much smaller. So although it's an amazing image, it has only just a bit more pixels than the original Hubble image from 1995. So knowing that, let's take a look at a detail on a high resolution part of it. So let's take a look at the top of this pillar here, right? Let's take a look at the top of that pillar. And this is the Hubble 1995 image. And this had these little fingers sticking up, which was really cool as the gas is being eaten away. You were thinking that these are the dense globules where stars might be forming. The other thing I'll draw your attention to is this jet here, okay? There's a star that is formed here, and there's a jet going off this way and this way, all right? And so when we got to the Hubble 2015, 20 years later, you can see the resolution improvement from Hubble. All right, going from WIF-PIC 2 to WIF-C3, kind of cool, the improvement. But you also notice, if you look at this jet here, that the jet actually extended over the course of 20 years. That's kind of cool, right? Then we go from Hubble visible to the Hubble infrared. This is, again, near infrared. All right, and you can see how the resolution goes down and how just so many more stars come out, all right, because we're seeing into it. You can see things like over here where it looks relatively solid in Hubble over here and over here, but actually the infrared view shows that there's not much there. You see the really dense pieces with the infrared. And here's where we can get to compare apples and apples, Hubble to Webb. Here is Hubble's near infrared, and here is Webb's near infrared. I hope it comes across on the video that there is a significant difference. You look at the resolution difference that you get going to the Webb Space Telescope. You also see a lot more texturing along the gas in here with Webb, again, because it has many more filters to pull out that detail. And finally, we go to the Webb mid-infrared, say goodbye to most of those stars. And you can see that it's significantly lower resolution in the mid-infrared, but you get all sorts of interesting detail, again, in the gas. One thing I want to point out to you is if I go back to the Hubble visible image, look at the surface of this brown gas here, right? As we go to the near infrared, it shrinks a little bit, all right? And in the near infrared, it's a lower level there. And when you go to the mid infrared, it gets even lower still, right? So what we are seeing is the wavelengths looking deeper inside the nebula, so that it grows as you go to the visible and it shrinks away as you go to the mid-infrared. Now, I could probably talk on this for hours because there's just so much detail in this, but let me just leave it there. And we will show you that there are 2 new images of the Pillars and Eagle Nebula from the Webb Space Telescope. These will tell us a lot more about the stars in there, because the near infrared sees many, many more stars than visible, and the gas and dust, how much gas and dust is required for star formation in that. All right, our speaker tonight is Stephanie Massa, and Stephanie is a scientist at the Space Telescope Science Institute working on the James Webb Space Telescope. She got her undergraduate degree from Boston University. And after that, she worked as a mission planner for the Chandra X-ray Observatory, which is run out of the Harvard and Smithsonian in Boston. She then went on to get her PhD here in Baltimore at Johns Hopkins University. And after the Johns Hopkins, she did a postdoctoral studies up at Yale University, and then a fellowship at Goddard Space Flight Center. So she's been going up and down the East Coast throughout her career. She's been here at Space Telescope. We've been lucky enough to have her for 5 years. And when I asked her, what does she do that's a little offbeat? Well, she says she does some panelists at sci-fi conventions. She has been several times to both Dragon Con and to Awesome Con. So we're expecting an awesome talk here today, Stephanie. Sorry, I had to do it. Ladies and gentlemen, Dr. Stephanie Massa.
All right. Thanks a lot for that introduction, Frank. And thanks to everyone for tuning in to hear about black holes. Okay, so black holes are probably the most enigmatic objects in the universe. And they are objects that I think rightfully captivate the imagination. And though they serve as an inspiration for a myriad of science fiction media, they very much have their basis in science fact. Black holes are a natural consequence of the description of gravity through the theory of general relativity, which says that mass itself curves space. So motions of objects, whether they be planets, moons, comets, even light itself, can be understood through its interaction with curved space-time. And the more massive an object is, the more that space-time itself bends. So taken to its extreme, you can have an object so massive in such a small region of space that the density becomes infinite and that causes a singularity. And this has interesting consequences for the escape speed, which is the velocity that an object needs to have in order to escape the gravitational pull of a body. And that escape velocity depends on that body's mass and that body's radius. So let's take the Earth as an example. The escape speed of the Earth is 11.2 kilometers per second. So if our little rocket ship here wants to lift off into space, it has to be able to travel faster than that speed. And if it's able to do so, it travels merrily into interplanetary space. If we replace the Earth with a singularity, then the escape speed becomes the speed of light, and nothing can travel faster than light. And so this is what we mean when we say that there's a black hole. Now, if our little spaceship here happens to cross the event horizon of the black hole, that defines the region where the escape speed is equal to the speed of light. And no matter how much our little rocket ship fires its thrusters, it cannot go fast enough to escape the gravitational pull, and our poor spaceship is doomed. So how do we get black holes? They are an end product of stellar evolution. Stars that are at least several times more massive than our sun go through life and end their lives in an energetic supernova explosion that sends a shockwave careening into interstellar space, heating the gas up to high temperatures. What's left is the core of that star. And if that remnant is dense enough, it can then collapse on itself to become a black hole. So if we have a black hole and not even light can escape it, then how do we actually see these objects? And to answer that question, we first have to define what it is that we mean by light. For those of us with sight, all the rich colors that we can see is just an overall small part of the electromagnetic spectrum. There's light at higher energies and light at lower energies. And most of this light we can't see with our eyes, but we could build telescopes to detect that light. And that becomes really important because objects throughout the universe give off light across the electromagnetic spectrum. So if we really want to understand the universe and our place in it, we have to build telescopes that's sensitive to all these wavelengths of light. This also becomes really important for understanding black holes because though we can't see them directly, we can see the effects that they have on their environment and their surroundings. And oftentimes those effects can't be seen in visible light, but in other parts of the electromagnetic spectrum. And here's one example. Many stars live in binary systems. So these are two stars that orbit around each other around a common center of mass. Our sun's a little bit of an outlier being in a single star system. Now, if both of these stars are much heavier than our own sun, then they will eventually end their lives as black holes. One star is likely going to be bigger than the other, so it's going to go through its life quicker. It'll go to a stage where it expands as a red giant, it'll go supernova, and then it'll collapse into a black hole. Now, at this point, the companion star is just merrily living its good life, converting hydrogen into helium in its core, doing what stars do. And as part of that, its atmosphere expands into space through stellar winds, and some of that material will find its way over to its companion black hole. We could fast forward this film, and that star will eventually become a red giant, so it'll expand, sending even more material out that will find its way to the black hole. And if we want to zoom in on what that looks like, we could see that in this right panel, where this material that comes out comes close enough to the black hole, starts to spiral into the black hole. It forms a disk due to conservation of angular momentum. And as that material spirals closer and closer to the black hole, it eventually falls in a process where the black hole grows in mass. We call this process accretion, and we call that disk of material that feeds a black hole an accretion disk. Now, this process of accretion gives off a lot of energy. The material rubs against each other, releasing lots of friction, which gives off energy and reaches temperatures that reach into the X-ray regime. So these objects do a great job of giving off X-ray light. And in fact, in the 1960s, this was one of the first X-ray objects from outer space that was detected. At this time, there were experiments that had X-ray detectors that were launched onto rockets to get above the atmosphere. Our atmosphere does a really great job of blocking out X-ray light from space, which is really good for our own health. A little bit challenging for X-ray astronomy because you need to get above the atmosphere to see X-rays. One of the first sources of X-ray light detected was in the Cygnus constellation. This object was called Cygnus X1, X-ray source in Cygnus. And we now know, as quickly learned afterwards, that what was being observed was X-rays from an accreting black hole that was stealing material from its companion star. We could go back to our picture of stellar evolution and turn the clock forward. Eventually, that companion itself is going to go supernova, and then you're left with two black holes. Now, at this point, there's no object around to feed either of the black holes to let them shine in light. So these black holes are now proper dark. How do we find these? We'll get back to that by the end of the talk. So this is a picture that explains black holes that are several times heavier than our own sun to maybe around 100 times or so heavier than our own sun. We call these stellar mass black holes. And where we have found stellar mass black holes are in these binary star systems that are giving off X-ray light. We see this in the center of our own Milky Way galaxy. Here's a beautiful image of the Milky Way center in X-rays. And we also see this in other galaxies that are relatively nearby, where we're measuring here the distance to galaxies in units of the amount of time it takes for light to travel from that galaxy to us. So these are X-ray images of two beautiful nearby galaxies. And you might see these points of light in these images. Some of those points are other X-ray sources. It might be neutron stars. But some of these are black holes in binary systems. There's another class of objects that we call supermassive black holes. These are millions to billions of times heavier than our own sun. And these live in the centers of galaxies. And compared to the galaxies that these black holes live in, they're really small. Could be anywhere from a factor of tens of thousands of times less massive than the galaxy to up to 1 million times less massive than the galaxy. And most of the time, these black holes are dormant. But sometimes we catch them in a phase where they're actively accreting matter, like their stellar mass X-ray binary cousins. And when we observe galaxies hosting these actively growing black holes, we call them active galactic nuclei, or AGN. And these are the types of objects that I study. So again, like their stellar mass cousins, these AGN do a really good job of giving off X-ray light, as well as light across the electromagnetic spectrum. And because this process is so energetic, we could detect galaxies hosting these growing black holes from nearby galaxies to the edge of the universe. So an example of how we could use X-ray light to find an AGN in a nearby galaxy is NGC 1365, which is a galaxy 80 million light years away. And this visible light image is just absolutely stunning. It's this barred spiral. If you were to observe the center of this galaxy in X-ray light, you see some of this like diffuse-ish emission that's from hot gas, but you see this bright point of light in the center. And that is showing us where this growing supermassive black hole lies. And we could also do this across the universe. On the right is a visible light image of the Hubble Deep Field. So it's a little piece of sky, about 1/12 the size of the moon, that Hubble observed for 10 days, detecting thousands of galaxies. The Chandra X-ray Observatory also looked at this region of sky, and that is the image that is shown on the left. And in that image, over 1,000 X-ray sources were detected, many of which are growing black holes in other galaxies. So another way to experience the Chandra X-ray deep field is through sonification, which is a process where data is translated into sound. So the colors of these points that you see here encode information about the energy of the X-ray source. The red colors are lower X-ray energies, and the blue and purple colors are higher X-ray energies. In the sonification process, those colors were converted into tones. So the low tones are for the red sources, which are lower energy, and the high tones are for the purple and blue sources, which are higher energy. So when I play this, we'll see a bar sweep up through the image, and that will tell you what the sources are that are producing the sound that you're hearing. So this provides another way of interpreting the data, a way that could be accessible for those who are blind or who have other types of problems with vision. So while X-rays provide a great probe for identifying supermassive black holes, there's a lot that we learn from observations across the electromagnetic spectrum, and they complement each other to highlight different physical processes. And this is well illustrated in a nearby galaxy, Centaurus A, which probably no surprise because I'm talking about it. Centaurus A hosts a growing supermassive black hole. So again, striking image of the galaxy with a very dramatic dust lane that cuts through the center of the galaxy. If we observe this galaxy in infrared light, the dust lights up. And we can start seeing behind that veil of dust, in particular, the point of light in the galactic nucleus, showing us where the black hole lies. And in fact, as you probably got from Frank's presentation at the beginning for the news updates, this is one of the reasons why infrared is such a powerful probe to learn about the universe, because it gives us that ability to peer through a dusty veil. Once we get to X-ray light, things start looking a little bit different. Here's the X-ray image, and we see this long, thin filament cutting through the galaxy. And then once we go to radio light, we see a thin filament that ends in these fluffy lobes. What the X-rays and radio are showing us are jets that are being launched from the AGN. These are accelerating particles to close to the speed of light through a mechanism that's either using magnetic fields to tap the rotational energy from the black hole. Might be coming from the inner edge of the accretion disk. We're still trying to understand how these jets form, but we know they're there. We know we see them, and we know that they are a part of some AGN that we observe, and that they could be extremely powerful. And when we put this all together, one of the striking things that jumps out is just how massive these jets are compared to the galaxy in which it lives. They're bigger than the galaxy. And it's remarkable to think about, right? When we compare the black hole to the galaxy itself, the black hole is just so much smaller, and it's over so much less mass, such a tiny area, but it could have this outsized impact where it's launching these energetic outflows that outstrips the galaxy. This is also an example of how, when we could combine data from different wavelengths, we have a more complete picture of the physical processes at play in this galaxy and what the black hole itself is doing. So everything we've kind of talked about so far has focused on how we could use images to identify black holes and learn a little bit about the physical processes. There's another technique that we use that's quite powerful called spectroscopy, where spectroscopy disperses the light into very fine wavelengths in a process that's very similar to how a prism disperses white light into its constituent colors. So this is a beautiful image of the Southern Crab Nebula. So not a galaxy, not an AGN, but an excellent visual illustration of how spectroscopy works. Elements shine at very specific colors or wavelengths of light, and that's determined by the laws of quantum mechanics. So in the top panel of images, what you're seeing are images of this nebula taken with filters that are centered at these specific wavelengths where these elements shine. These are ionized species of oxygen, hydrogen, nitrogen, and sulfur. The bottom panel is the spectrum, showing discrete sharp lines at these very specific wavelengths, again, corresponding to the light coming from these elements. And this is why we could use spectra as fingerprints of elements to determine the chemical composition of the object that we're studying. Spectra also tells us what the energy source is that's lighting up the gas that we're observing. And it does a whole bunch of other great things too. So here is a spectrum of a class of AGN. Very similar conceptually to what we saw on the previous slide. The X or horizontal axis is showing us the wavelengths of light. The Y or vertical axis is showing us the amount of energy being given off at each wavelength. And we see these sharp lines in the spectrum. These lines correspond to ionized species of hydrogen, carbon, magnesium, oxygen. And what this spectrum is telling us is that the energy source lighting up the gas is an accreting supermassive black hole. Other processes in galaxies don't cause these features with these specific characteristics, whether it's the intensity of the line or the width of the line or the relative intensities of the lines compared with each other. So it becomes a very powerful diagnostic to identify galaxies hosting growing black holes. And as you might be able to tell, some lines are wider than the others. And that's because those lines are coming from gas that is closer to the black hole, so it's orbiting more rapidly, while the lines that are more narrow are coming from gas that are further away from the black hole, so it's orbiting slower. So again, using spectra are almost a gold standard for identifying which galaxies host growing supermassive black holes. And this is One technique that I use in my research, just this past month, I've been on several observing runs with two telescopes where I have been taking spectra of objects that I believe are AGN, and the spectra are what tell me whether or not that's true. So that's one way to study these objects is to identify promising sources and then follow them up with telescopes. Another technique that we could use is to use telescopes that act completely as survey telescopes, meaning that what they do is scan the sky, they take images, they take spectra of what they observe, and they store all that data in archives that become available for astronomers to use for analysis. And an example of this is the Sloan Digital Sky Survey, which has been taking data and one of any, it's been through 5 iterations since 2000, but it's been operational in some format for over 2 decades now. And just from the Sloan Digital Sky Survey itself, we've discovered over 750,000 black holes in other galaxies, some from galaxies nearby and some from galaxies really far away. And Sloan Digital Sky Survey holds a special place in my heart because part of my PhD thesis was based on a sample of galaxies selected from Sloan, and I still use data from Sloan in my research and up to today. So these surveys are a great way to build up a statistical picture of black holes from early cosmic times to the present day. We could also use in-depth spectroscopic observations of individual objects to learn about the physical processes in these systems. And this is something else that we've been doing for decades using telescopes from ground and from space. And our newest telescope to join the family is no different. JWST, the latest flagship observatory in space, launched in December. It studies the infrared universe. And this telescope is indeed a game changer. It's undertaking both surveys, like we saw at the Hubble Deep Field. JWST is also doing deep surveys, and it's also doing in-depth studies of individual objects. And from the in-depth spectroscopic studies, we can learn about the chemical composition of galaxies and identify which of these are hosting supermassive black holes. And as a demonstration of this is Stephan's quintet, which is one of the first science observations released from JWST in July. Now, this is a stunning image, and there's just so much that could be said about this image. We're seeing these 5 galaxies, 4 of them are gravitationally bound, lots of cool stuff going on in this image. But I want to focus on this top guy here, NGC 7319. Probably no surprise. The reason why is because it hosts a growing black hole in its center. This galaxy was observed with the JWST spectroscopy modes as a demonstration of JWST's spectroscopic capabilities. In the mid-infrared, we obtained spectra from above the nucleus of the galaxy, which is gas that is hot and ionized from the accretion disk, this outflowing wind, where we're seeing ionized species of iron, argon, neon, sulfur, oxygen. The bottom spectrum is from the nucleus itself, where we're probing colder, denser dust that enshrouds the nucleus, seeing molecular hydrogen and seeing silicates. In the near-infrared wavelengths, we see atomic hydrogen, which is tracing structures of this outflowing gas. Iron, which traces the location of the hot gas. And again, the colder, dense dust traced by molecular hydrogen, which itself may form a reservoir of material to feed the black hole. From spectroscopy, we could also learn about the gas motion and speed. Anything here that's showing a blue color represents gas that's moving towards us, while anything showing a yellow color represents gas that's moving away from us. So from spectroscopic observations like these, we learn about how black holes are fueled and how they give off energy to affect their surroundings and maybe even inject energy that guides the evolution of the galaxies that they live in. And we do this by mapping out the chemical composition and the motion of material both near and far from the black hole. Another great thing that we could get from spectra is to measure distances to these galaxies, where we could use the fact that the universe is expanding and the Doppler shift to our advantage. So an example of the Doppler shift is if you hear an ambulance with a siren go by. As that ambulance moves further and further away from you, the pitch of the siren sounds lower and lower and lower. And that's because the sound wave coming from that siren is moving away from you. It's traveling a greater distance. So the wavelength of sound is getting stretched to longer and longer wavelengths. We know the universe is expanding, and as it expands, it takes galaxies along for the ride. So the light that comes out of these galaxies travels through space, which is expanding, which causes the wavelength of that light to shift to longer wavelengths. So galaxies that are closer by will have a smaller shift in wavelengths. Galaxies that are further away will have a larger shift in wavelengths. And taken to its extreme, you could have galaxies at the farthest end of the universe that are made up of stars that are young, giving off lots of energy at ultraviolet wavelengths that travel through the whole extent of the universe to get to our telescopes here on Earth. And because it's traveled so far, the wavelength of the light has been shifted all the way to the infrared. So when we observe spectra from other galaxies, we will see that these emission features will be at redder wavelengths than they would be if we were observing them in the lab. So by comparing the wavelengths at which these lines appear in these galaxies with where they should be, gives us a measure of how much the universe has expanded, which gives us a distance measurement to that galaxy. So here's an example. Again, going to an early release image from JWST, another stunning image. JWST is just awesome and what it's giving us. So in the left, we are seeing an image of a galaxy cluster, thousands of galaxies, JWST's first deep field. Again, so many amazing things we could talk about in this image. This part of the sky was also observed with a couple of the spectroscopic modes on JWST, which being shown here are some of the galaxies that were observed with the NIRSpec instrument, which got spectra for tens of the galaxies in this field. So the middle panel shows close-up images of 4 of these galaxies. The right-hand panel shows the spectra for those galaxies. So what I want to draw your attention to is this set of features here, these lines. What you're seeing is ionized oxygen, O3, it's been ionized twice. By the way, my favorite emission line. And you're seeing ionized hydrogen. And as we go down panels, we see that these features get shifted to longer and longer and longer wavelengths because they're coming from galaxies that are further and further and further away from us. The galaxy on top is at a distance where light has traveled 11.3 billion years to reach us. And on the bottom, the light has been traveling 13.1 billion years to reach us. So these are galaxies, and it's fair to ask, what about AGN? What about galaxies hosting growing supermassive black holes. What's the most distant AGN that we know about so far? And so far, the record holder is an AGN where it's taken light 13 billion years to reach us. So not as far away as the most distant galaxies. And this is a beautiful artist rendition of what a growing supermassive black hole looks like. The image is perhaps a little bit less impressive, but it does encode a lot of information. All right, so in the three left panels, we're seeing this object in visible light. The two right panels, we're seeing this object in infrared light. The cyan circle shows us where the source is. In the visible panels, you see a whole lot of nothing within that cyan circle. In the infrared panels, it gets much brighter. We see an object there. Now, one explanation for this could be that this object is so far away that the ultraviolet to optical light from this galaxy has traveled such a long distance that's been redshifted into the infrared regime. And to confirm that, you need a spectrum. And indeed, the spectrum of this object shows ionized species of carbon and magnesium. And because of the width of these lines, we know that this gas is being energized by a growing supermassive black hole. And from these lines, we're also able to measure the distance to the galaxy. Another very interesting thing about this source is that the black hole in this galaxy is at about 1 billion times heavier than our own sun. Now, we've seen black holes that massive in other galaxies, but what's interesting here is that the universe was only 670 million years old by the time this galaxy was in existence with a black hole this massive. How did this black hole get so massive so quick? It's not going to be from feeding stellar mass black holes because there's not enough time to dump material on them to get them this big. So there has to be some other formation mechanism. And indeed, that's one of the questions that we think JWST will be able to answer, because JWST will find even more distant galaxies, even more distant black holes that will have a better statistical picture of the demographics of what these first generations of galaxies and black holes look like, and then compare that with different theoretical models to understand their formation pathways. As some of you might know, astronomers are quite excited about JWST data finally being available and things looking so good. And certainly after the first couple of months when science data were released to the community, there has been a lot of speculation that some really distant galaxies have already been detected really early on in the life of the mission. So one thing that I do want to say is that those objects are candidates. They are objects that, based on imaging and some model fits, could potentially be galaxies really far away. What we need now is spectroscopy of these candidates to be able to measure the distances to them and confirm if they are at the distance that these other data seem to indicate. And what's more interesting for me is not only how far away are they, but do any of them show signatures of AGN activity in their spectra? Over the next couple of months, years, we'll be getting lots of spectra of a whole bunch of galaxies. So we'll be knowing more about this soon. All right, so we've talked about supermassive black holes in nearby galaxies and in galaxies far, far away. Is there anything closer to home? The answer is yes. In our own Milky Way galaxy in the center, 27,000 light years from where we are, there lurks a supermassive black hole called Sagittarius A star. Unlike these AGN that we've been talking about, this black hole is largely dormant. We know about its existence due to years and years of dedicated work from a couple of research groups, one of them being the research group led by Andrea Ghez from UCLA, who have spent years measuring the motions of stars in the galactic center, mapping out their orbits, and calculating how fast they're orbiting. Now, you can't see anything that they're orbiting around, but we have their speeds. And just by using Kepler's laws, you could calculate the mass of the object that these stars are orbiting around. When you do that, you get a mass that's 4.3 million times heavier than our sun. So here we have evidence of a supermassive black hole. So while this black hole is not an AGN, some of the stars that do orbit around the center give off stellar winds. Some of those winds do find their way onto the black hole. So we see some small activity there, very wimpy compared to these growing black holes in other galaxies. It's like a factor of a billion difference, but some activity there. And in fact, we've gotten a closer look at Sagittarius A star from the Event Horizon Telescope. The Event Horizon Telescope has given us our closest views humanly possible to a black hole. And they're able to resolve really small scales. And the reason that they're able to have this high resolution is because of a technique they use called interferometry to build up a large virtual telescope. Now, in astronomy, if you want to see really small scales and have great resolution, you want to have as big of a telescope as possible. With interferometry, you achieve this by having an array of telescopes. And that's illustrated a bit on this view graph. It's a little bit busy, but we'll go through it step by step. So the top panel shows how when you have two radio telescopes and you increase the distance between them, you've increased the baseline of this virtual telescope. So you get to a larger baseline, the image becomes sharper. The next panel down is showing that what's observed by radio telescopes is an interference pattern that could be analyzed using a mathematical technique called a Fourier transform. And the bottom panel is showing that as you add more and more telescopes to the array, get more data points, and as the Earth rotates, it fills in the space between the data points, and then you're able to reconstruct a really sharp image of the object that you're observing in outer space. The Event Horizon Telescope uses an array of telescopes around the globe to create a large virtual telescope. So in essence, they've turned planet Earth itself into a telescope. It's pretty awesome. Earlier this year, the collaboration released this image of Sagittarius A star, the supermassive black hole in the center of our galaxy. So we see this donut with a dark center. That dark center is the black hole shadow. The space around a black hole is warped due to the mass of the black hole. Again, general relativity, large masses warp space. So the light rays from any light that's behind it are traveling through this warped space-time, causing the center of this image to be dark. This black hole shadow is about 2.5 times the size of the actual event horizon, but it's as close to a black hole that the laws of physics allow us to resolve. You might remember several years earlier, the Event Horizon Telescope released an image where they observed a galaxy M87 that has its own supermassive black hole that's launching this jet that's thousands of light years long. And if you want to play the game of name that black hole, I mean, I kind of give the answer away. I labeled the black holes, but it's really interesting to do this side-by-side comparison because there's so many similarities that we see in these two images, right? We see this circular ring that's due to that bending of space-time near the black hole. We see that the rings are largely symmetric. We see brighter parts in both rings. Those brighter parts show us where matter is moving towards us. The darker parts are showing where matter is moving away from us. And both of these images represent the small scales that we can possibly see around a black hole. And it's kind of mind-blowing when you think about it, when you think about the different distances involved. Sagittarius A star in our galaxy, 27,000 light years away. In M87, we are resolving these scales at a distance of 55 million light years away. What's also interesting is that Sagittarius A star, this black hole, is 1,000 times smaller and less massive than the black hole in M87. And this is what a factor of 1,000 means. Our whole solar system could fit within the black hole shadow of M87. And again, think about this. We could resolve the scale of something the size of our solar system in an object that's 55 million light years away. That in and of itself is mind-blowing. In Sagittarius A star, the outer edge of the ring shows us where is the same size as Mercury's orbit. So very different absolute size scales, very different distances to these objects, but the same physics. And we're resolving the same scales relative to the size of the black hole. All right, so we've found black holes from several times the mass of our sun to billions of times the mass of our sun, from our own galaxy to the furthest reaches of space. We can use spectroscopy to observe a black hole's effects on its environment and how material can be fueled into the black hole. And we've resolved the smallest region that's possible to see around black holes. And we've done all of this using light. There's another messenger of information that we could use to learn about black holes, and that's through gravitational waves. Gravitational waves are another consequence of general relativity. They're ripples in space-time from the most energetic processes in the universe. So massive accelerating objects that collide will cause these ripples to propagate at the speed of light in all directions, carrying clues about their origins. So if you think back to the beginning of the presentation where we had this binary star system that evolved to the point where all that was left were these black hole remnants, not giving off any light. If those black holes in spiral and collide, we could use gravitational waves to detect these objects. And we now have observatories that can detect gravitational waves. The LIGO Observatory is made up of 2 detectors in the United States, one in Washington State, one in Louisiana. And they started taking data in 2015 with the first gravitational wave discoveries announced in February of 2016. And about a year later in 2017, the Virgo interferometer in Italy came online. Now for gravitational wave astronomy, it's really important to have more than one detector. Though that animation I showed on the previous slide looked pretty dramatic with the ripples coming out from the inspiraling objects, the actual signal from gravitational waves is really, really tiny. So they're very challenging to detect, and sources of noise become the most prominent thing that are actually detected at these observatories. But these sources of noise are going to be local in origin. It could be a tremor in the earth, an extremely slight earthquake. Maybe it's traffic traveling by miles and miles away. But you won't have the same source of noise in detectors that are far apart geographically. So if you detect the same signal in multiple detectors with a time delay that's consistent with the light travel time between those detectors, that gives you a higher confidence that that signal is astrophysical in origin. And that signal, the frequency of the signal that's detected, tells you about the masses of the objects that collide and the mass of the final object. So here's a way to kind of that you could internalize it, because you can convert that wave signal into sound and hear the difference. All right, so the gravitational wave signal from December 2015 has a higher pitch than that from September. And that's because the signal from December was caused by black holes that have a lower mass than the one from September. So that frequency of the signal encodes information about the masses of the objects that collide and that final mass. As of now, we have about 50 gravitational wave signals that have been detected since observations started in 2015. And this graph shows the masses of compact objects that have been observed to date. So as you go higher up in the graph, the mass increases, and these are in units relative to the mass of our sun. So the yellow and orange points are neutron stars, so just ignore those. We don't care about those. I mean, maybe you care about those. I think they're kind of cool, but really I care more about black holes, especially for this talk. The yellow, the pink circles, these are black holes that are in binary systems that are giving off X-rays, and that's how we've detected them. So these are the black holes that we know from X-ray light. The blue circles are the black holes that have been detected through gravitational waves. And you might see that there are three that are connected by arrows. So what that is showing you are the masses of the two individual objects, black holes, before they merged, and then the final mass after they collided. So one of the really interesting things about these detections and about this graph is that the blue points, by and large, are above the pink points. From gravitational waves, we are detecting black holes that are more massive than those that we detect in X-ray binaries. This is a whole part of the population that we were ignorant about prior to 2015. And in fact, some of these detections are challenging some of our theories about stellar evolution. So since March of 2020, the operations at LIGO and Virgo were halted because of COVID, and they've been going through a process now of upgrading the detectors. The next observing run is planned to start up again in March of 2023. And it will be joined by a Japanese facility called Kagra. So now we'll have 4 gravitational wave detectors over the globe, which is great. The more detectors you have, the better able you can triangulate where on the sky the gravitational wave detection is coming from. So on the ground, we could only observe certain frequencies of gravitational waves. You know I care about supermassive black holes. We can't detect those from the ground. For that, we need to get into space. The gravitational waves given off by colliding supermassive black holes are much lower frequency than what we could detect on the ground. So the LISA Observatory, which is slated to launch in the 2030s, it is led by the European Space Agency with contributions from NASA, and it is a satellite of 3 gravitational wave detectors, each spacecraft separated by about 1.5 million miles, which is just mind boggling to think about, right? JWST is a million miles away from us, and these three satellites are going to be even further away from each other, but flying in perfect formation to detect these teeny tiny ripples from colliding supermassive black holes. These types of observations will be really helpful to learn about how mergers of galaxies and black holes play a pivotal role, perhaps, in some forms of galaxy and black hole coevolution. So it'll be very cool once that's working. All right, so go back to the question that I posed as my talk title. How do we see that which gives off no light? Well, one way is that we can use light. We could use light to observe black holes' effects on its surroundings, whether it's from black holes feeding on any unlucky matter that gets too close to it that can escape, that gives off a bunch of energy before it disappears forever into the black hole, or if it's by mapping out the motion of nearby stars or gas or dust and using orbital mechanics to be able to measure the mass of an object that we can't see. We could use a completely different messenger of information, gravitational waves, to learn about objects that inspiral and collide. And really, it's this combination of multi-messenger astronomy where we have a much more comprehensive view of the energetic universe. And there is a lot that we've learned about supermassive black holes from being mere curiosities decades and decades ago to now being a foundational part of galaxy evolution and modern day astrophysics. But there's still some mysteries. How did the first supermassive black holes form? What is the full population of black holes across all mass ranges, including those that are really difficult to detect? What role do black holes play in shaping the galaxies that they live in? And what controls the feeding habits of black holes? Most galaxies that host supermassive black holes, those black holes are dormant. Why do some of them turn on? Why are those feeding? How does material get to them? And why do they stop feeding? And in the past few years, we've learned a lot due to an array of multi-wavelength telescopes from ground and from space, as well as observatories that could detect gravitational waves. But the future is even brighter. The next generation of telescopes will really push the field forward. And we've been saying for years now as a community that JWST is going to be awesome. It's going to tell us so much about the first galaxies and the first black holes. And after an intense year for those of us supporting launch and commissioning, we are thrilled to say that the performance of this telescope is phenomenal, exceeding some of our even most ambitious expectations. So we know JWST is going to deliver on these promises. And from those observations, we're going to understand how black holes evolved from early cosmic times to the present day and how they shape galaxy evolution. It's going to be an exciting few years. So stay tuned for exciting updates. Thank you.
Oh, and thank you, Stephanie. It has been a joy over my career, over the years I've been doing astronomy, to watch black hole talks go from these theoretical ideas to a little bit of observations and X-ray binaries and stuff until we finally have some real serious observations to discuss. That's got to be gratifying for a researcher in the field as well.
Yeah, I mean, it's just so funny because like we can't think about modern day astrophysics without black holes, right? And to think about just how far it came from the 1960s when the first quasar was discovered, and it was like, what is this quasi-stellar source that's giving off radios? And what's this all about? And then finding out, it's like, oh, well, that comes from beyond the galaxy, and we think it might be a
Yes.
black hole. It's like,
Yeah, the
Amazing.
pathway in science is long and it takes lots of twists and turns. But when you've got something and you get the EHT images, you go, yeah, we've really gotten quite an amazing progress over these decades.
Absolutely.
All right, so I get to ask the first question.
All right.
And you showed AGNs and you talked about AGNs, and then you showed these jets. Yeah, and
Yeah.
one of our astute viewers wanted to know, how do the jets from such a small object, you emphasized how small these black holes are, get so collimated that they stay like stretching across an entire galaxy? How do you collimate jets so carefully?
How do you collimate jets so carefully? So we think magnetic fields play a role. So what we're seeing is particle acceleration. And so these particles will accelerate by rotating around magnetic field lines. And this is one of the ways that we could distinguish between jets and outflows. It's just by how collimated or how thin it is. And we really think that it's the magnetic fields that is somewhat shaping the jet shape to be narrow.
Right, and also, I mean, so the magnetic fields are wound up by that accretion disk, right?
Right, right.
Okay. All right. So basically, I'm not a specialist in this, but I like to think of it as the accretion disk is just winding this up, getting it so tight. It's almost like, twisting a little candy. You get those really tight things, but since it's doing this at relativistic speeds, it can get it into a really long jet out of that. Yeah, that's cool. And as always in astronomy, we don't know, it's got to be magnetic fields, right?
Absolutely.
But here is one place where that's not a cop out. Okay.
And to have that be the answer to my first question, it feels like no, I don't think this is really a cop out, guys. I think
No,
this is
no, no.
real.
It's actually real. All right. We've had a bunch of questions and a bunch of compliments on your talk in the chat.
Well,
Grant, you want to turn on your video and let us know which questions you've picked out from the chat. Welcome,
Yeah,
Grant.
absolutely. Hello, everyone. So yes, the chat has been great tonight. Thank you, everyone, for tuning in and asking questions. We'll start off here. Literally at the beginning. What sort of effect do you think black holes had on Big Bang / formation of the universe? Like, where do they fit into the giant
Primordial.
Yeah.
primordial. Oh, okay. So yeah, primordial black holes are a whole other topic. And I know some people have been working on this. I've not, so it's not one of my fields of research, so I don't really keep up with that. Yeah, so the objects that I study by and large are these things that are the end products of something that formed after the Big Bang, right? So for the
Right.
supermassive black holes, they probably formed from larger seeds in the stellar mass black holes. So you had to have already gone through the Big Bang and had a dust cloud or something else, or intermediate mass black holes that merged and combined to form bigger black holes. When we're thinking about the very first generation, the primordial ones around the Big Bang, that is a whole nother ball game.
Yeah. Okay. That's, you're not expected to be an expert on absolutely everything in the universe. Although those of us in the outreach office have to pretend to be experts in almost everything. Let's see. There was a question. There was a question sort of related to something like this. I know it might be off topic, but the gamma ray burst that just happened last month. Somebody was asking about that. 221009A. They're said to be the biggest of all time.
Yeah.
Any new information on that, or do you want to explain it to our audience a little bit?
Yeah. So, I mean, there's not much more than I know about that, other than Swift detected this super energetic gamma ray burst, I think at a time when there was like a conference on gamma ray bursts happening. Like
Exactly.
the timing was just kind of
like it happened
really
on
ridiculous.
Saturday and the conference opened on Sunday.
Yeah. Yeah. Like, oh man, to be a fly on the wall at that conference, it must have been amazing. So I don't know what the latest on that is. I know that super energetic, very exciting. I know I've asked some people like, well, what is going on with that? I think they're still trying to figure it out.
And it was a long gamma ray burst. They said they were detecting it for like 10 hours, right?
Wow. Yeah.
10 hours for a gamma ray burst is one of the longest I've heard of. I'm not an expert in
Yeah.
that field as well. So,
Yeah,
okay.
these things usually last for like seconds or minutes at
Yes.
the longest.
So,
Hours is crazy.
yeah. And the other thing that I read about it, that it was about 2 billion light years away, which, sometimes for gamma ray bursts, that sounds really, really far away, but for some gamma ray bursts, that's actually relatively close, right?
Yeah.
So getting this strong. All right. So that's another question we can strike off the list, because I didn't think there was anything new. But the observations sure will be ongoing. All right, Grant, what you got?
All right. At what location in the AGN do relativistic outflows originating from the active galaxy get accelerated and highly collimated?
Wow, we've got some good questioners.
Yeah, those are really good questions.
Well stated.
Yes, this might be a ringer. Okay, so when we think about an AGN, we think about it kind of like in different pieces, right? So you have a black hole, you have the accretion disk feeding the black hole, and then right above and below the accretion disk is this region where, if we think back to that spectrum where we saw these lines in the spectrum that were wide, those lines are broad, so we call it the broad line region. So this is a gas that's close to the black hole that is orbiting rapidly, and that's causing the lines to get broader. And it's from this region that we do see winds coming off the accretion disk that propagate into the host galaxy. So these winds don't necessarily get very collimated. If we think about collimation, we're thinking more about jets that are getting collimated by the magnetic fields. But we do kind of see that these are in a preferred direction because the accretion disk is a disk. The winds are going to come off above and below the disk and not from the sides. Another thing that we also think about around AGN is that around the accretion disk is a torus of dust and gas, which obscures your view to that central region. So sometimes we don't see that central region of the accretion disk or the outflows or the broad emission lines because this object is oriented such that we're looking through that torus, all that is blocked. So we only see the stuff that is above and below by several parsecs. A parsec is something like 3 something light years. So sometimes we could see some activity there, some type of outflow activity, though not as rapidly as the stuff that's closer to the black hole.
Okay, yeah, that's a really good an important point, that there are many different scales when you talk about these AGN structures, and the different emissions come from different scales. And you also mentioned that it's blocked, and so there's the difference between the blazars and the QSOs and the liners and all those different emission regions for AGN. So the angle at which you're viewing it, which is something you wouldn't necessarily think of, plays such a big role in your field.
Yeah, absolutely. That would be a whole nother talk.
Yes, that would be. I think I sat through that talk about 15 years ago.
A good reminder for people in the audience, we've done lots and lots of these. If you have a question, we've probably covered it.
Okay,
all right.
What else you got?
So I actually like this one quite a bit. So black holes can collide and they lose mass in the collision. Does that mean something actually escapes them? Do they trade material?
Yeah. So if you do the math, right, and you think about these gravitational wave events that we've observed, and you add up the mass of the 2 progenitors, the 2 black holes that were there, and then the mass of the final object, there's a difference. Some of that goes into energy. E equals mc squared. So some of that mass gets converted into energy, which is given off by gravitational waves.
Right. And that actually brings up another question somebody asked. I mean, there's a tremendous amount of energy from this black hole collision being given off, but by the time it gets to our solar system, it's really diluted. So somebody was talking about a Star Trek episode where I guess some sort of wave passed over the Enterprise or whatever, and everything got distorted and everything. Can you clarify that that's not really what happens with the gravitational waves that we've observed?
I mean, this would make detection so much easier, right?
It would be fantastic.
You wouldn't have to do these things that are 10 to the minus ridiculous, like
Yes.
strains that they're, trying to find instead. Yeah, it's not actually what happens. It
Yeah.
it would make some people's job easier, but not
Do you,
what
do
we
you, do you
get.
happen to know the actual scale? Is it a femtometer or something like that?
Something
I
like
don't
that. I don't remember off the top of my head. It's really tiny.
know.
Yeah.
It's 10 to the minus ridiculous. I love that
Yeah.
phrase. So the amount of spatial distortion is immeasurable. It's, on more on the atomic scale, right?
Yeah.
Okay.
Yeah.
Just gonna get that question answered. Go ahead.
Two wonderful phrases tonight. It was 10 to the minus ridiculous. And what was the other one? Candy Galley or yeah. I love it. I love it. All right. Less of a question and more of a point for further discussion. Let me pull down a little bit here to grab it. So if the jets are collimated by a magnetic field, would that make them ionic, which would change the spectroscopy?
So, yeah, okay. So, I mean, it's what we're seeing when we observe jets is synchrotron radiation. So, kind of the spectra that I was showing of AGN, that's not going to be from a jet. That's going to be from gas, like in the galaxy itself. The spectra for jets are they just look different. It's from a different physical process. So again, it's particle acceleration. So you have to start thinking about particle physics a little bit and thinking about the different origins for particles.
Right. And I'm used to thinking of observing jets in radio waves, right?
Yeah, yeah.
So that you're not really looking at spectra in the radio waves, right?
Right. Right. Like
It's
you'll get like a spectral energy distribution, right? You'll get, so you can also see jets in X-rays, but like kind of a similar, like you'll have like these seed photons probably from the cosmic microwave background that inverse Compton scatter off of plasma, causing these jets. But so what you would get are um, you would get the amount of energy at some discrete wavelength. So it won't be like the kind of the same information that you get from a spectrum, but you get like a very, very, very low resolution spectral energy distribution that you can fit with different models.
right. But I think the original commenter is correct, in saying that, all right, if they're being accelerated by magnetic fields, they have to be charged.
Right. Oh,
So,
yeah,
so,
yeah,
yeah.
yeah.
So just clarify on that point. Okay.
Cool.
I had a question I wanted to comment on because you've been using Sloan Digital Sky Survey, and a lot of researchers these days are using the Hubble archive, and they will be using the Webb archive. Can you just make a comment on how the development of these very large archives that researchers can mine has helped astronomy, or hindered astronomy if you think so, but I kind of think it helps it.
Almost too much data to get through. But no,
Yeah.
it is just so it's so amazing because I mean there's several things that you could think about. If you think about a survey telescope, something like the Sloan Digital Sky Survey, there will be several science questions that are posed that you'll say data from this survey will help answer, and that's why we need to observe these types of objects and take these data to answer these types of questions. But the applications for what could actually be solved with that data set go well beyond that original pitch for why you need that telescope or a certain observing plan. So you're really only limited by the creativity of people, of astronomers to ask big questions. And that could be anything from statistical studies where you need big data and you're looking for trends. It could be, hey, I discovered something kind of interesting. Is there any other data out there of this object that I didn't even know about? Go through archives and find that. And so even for things like the Hubble archive or the JWST archive, those are observations by and large where astronomers have said, I want to look at this object or this patch of sky for this reason. It's not like these big holistic, let's just study a whole big part of the sky and just grab as much data as we can. These are kind of to answer very specific questions, but then the value of those data sets to the community who might come back a year later, 2 years later, 20 years later, to then look at that data to answer other questions. I mean, like it helps in ways that the original observing team probably never even thought about.
And I think forward to the Rubin, and we're going to get a 10-year monstrous data dump that we'll be going through for probably the rest of this century.
Seriously.
And I also think back to the discovery of Uranus and Neptune, et cetera, going back into the old Flamsteed plates to try and see, oh, somebody actually did see this, 70 years before anybody ever thought to go look for it. So
exactly.
you as a beneficiary of one of these great surveys, I just think great to hear your view on it. Yeah. Okay, Grant, all
right? 2 more questions.
Two more questions.
Just about right.
Sounds good.
All right. With all the different techniques of detecting black holes that are available now and what is known about their biases, can we estimate the distribution of black hole masses or spins in the universe?
Yeah, so that is a really good question. And
chat on it.
Yeah, seriously. And the answer is yes, kind of. There are definitely papers published every couple of years where people will use survey data to say, again, look at a patch of sky, assume it's representative of a certain population, and then map out saying, we've detected these many black holes at all these different distances. You could then use that to say, here's how we think this population has evolved over time. So getting to that of like, what's the distribution of black hole masses? And the more that you could combine data from different selection techniques, perhaps you can mitigate the biases with any one technique to get a more comprehensive view. That being said, it is complicated because then each one has biases. So then how do you combine stuff knowing that they all have biases and they have different selection techniques? So it's complicated and there are some limitations, but it's definitely stuff that people do work on. And that is an interesting thing to do, is to compare what you get using one method with a different method and just seeing where the consistencies are and understanding what it is that you might be missing in some studies versus other studies. There's actually probably going to be a paper that I'm co-author of coming out sometime within the next few weeks that does this. We just got the referee report on it, I think today. So it is a really cool thing to do. For getting the spins of black holes, that is a little bit more challenging, just because sometimes it's hard to definitively measure the spins of black holes. And some of the ways that are used, not everyone agrees that those techniques uniquely measure spin. You could get some of these features by other processes. So that's a little bit more challenging.
Well, one of the things that I thought was fascinating about the stellar graveyard, like you showed the stellar graveyard thing, is that we're getting up to actually knowing of mass black holes at 150 solar masses, right? We didn't have evidence for anything like that a few years ago. So our speculation that we could have 300 solar mass black holes might not be as so much speculation anymore.
Yeah, it's really cool. Like the big one, the most massive signal where they announced that, I think September of 2020. Like it was really cool. Like not only was like this black hole mass, you said like around 150 times the mass of our sun, but even the masses of the progenitors, the two things that collided, some of those were like, how do we get black holes that big?
Exactly, right.
This doesn't make sense, guys. It's really cool.
All right, last question, Grant.
All right, I will finish us out with this one. So what was it that got you originally interested in astrophysics? And what path would you say someone getting into it newly should do? I mean, you knew it was coming.
Okay. like these questions. All right. So like the short answer is I always thought outer space was cool, and then I never grew up. And so I just kept on, when
Growing up is a trap. I'm just throwing that
yeah,
out there.
yeah, absolutely, absolutely. So when I was in high school and looking at colleges, I was like, I want to major in astronomy, and so I just applied to astronomy programs, and just kind of kept on going from there. So for someone new wanting to get into it, I'd say there's just like so many opportunities out there, so much more than when I started out, because now we have the internet and now we have all these other things, like wonderful outreach activities to engage people.
You mean you couldn't control F your dissertation when you were looking for things? I mean,
Well, I was thinking more like more younger, when you're kind of like more high school age, which was, yeah, I wasn't writing any dissertations then. So one thing that I would recommend is look for intern opportunities, and apply for those. There are also websites that have online tutorials about, they'll give you a data set to play with and a tutorial of how to work through that data set. So those could be a lot of fun to look at. I think STSCI might have some of these through their archives. I know Sloan Digital Sky Survey has some of those. Get some experience with coding, because we do a lot of coding to analyze data. And yeah, just keep on listening to cool and fun talks, and look for opportunities for internships and other things.
Yeah, and you can't emphasize enough the ability to do your mathematics, to do your coding, and I like to say just to solve problems, okay?
Yeah.
Because astronomy is about encountering things that are just out there, right? And so you've got to be able to think laterally. You've got to be able to think outside the box for a lot of astronomy. So
Yeah, a big thing is grit, right? Like it gets hard. The more you're willing to stick with it and work through challenges, like that's really a good trait to have.
all right. Okay, so that's all the time we have tonight. Next month, December 6th, high energy astronomy with the Swift Observatory. And so that gamma ray burst we just talked about, discovered by Swift, you'll hear about that next month. Steve Kirby from Penn State University. Until then, enjoy looking up, enjoy exploring your universe. Take care, everyone.